Hello everybody. In this video we are going to be looking at the solutions to the honors sound homework problems 1 through 5. Well, let's get started with problem 1. A sailor strikes the side of his ship just below the waterline. He hears the echo of the sound reflected from the ocean floor directly below him 2.5 seconds later. How deep is the ocean at this point? And assume that the speed of sound in seawater is 1,560 meters per second. So the total time it takes for the sound wave to come back up off the ocean floor is 2.5 seconds. Now, I know that if here is my ocean, here's the ocean, here is my boat. There's my boat. You guys remember how great of an artist I am, don't you? All right, and here's my sailor. Here's my sailor. And let's just do the bottom of the ocean right here. This obviously is not drawn to scale. If he hits the side of the boat just below the waterline, and the sound wave has to travel from the boat to the ocean floor, then reflect off the ocean floor and come back to the sailor. Now, the sound wave has to travel all the way down and then back all the way up. If we want to know just the distance, so all we're trying to find is the distance from the boat to the ocean floor, I need half of that total time because I just need to know the time it takes the sound wave to reflect off the ocean floor and come back up to the boat. So the total time, or the time I'm going to use, is going to be 1/2 of the total time. So 1/2 of 2.5 seconds is going to equal 1.25 seconds. I know my velocity is 1,560 meters per second. So now I have the time and I have the velocity. I can find my distance because I know the distance is equal to the velocity times the time. Another oldie but a goodie from way back when, but you guys know these formulas never go away. So I multiply my velocity of 1,560 meters per second times my time of 1.25 seconds, and I will get a distance of 1,950 meters, or 2.0 times 10 to the third meters rounded to 2 significant figures. And we need 2 sig figs because my time value is 2.5 seconds. Part A of problem 2 asks us to calculate the wavelengths in air at 20 degrees Celsius for sounds in the maximum range of human hearing from about 20 hertz to 20,000 hertz. My temperature in this problem is 20 degrees Celsius. The lower end of the range of human hearing is my first frequency, and that's at about 20 hertz, or 2.0 times 10 to the first hertz. The upper range of human hearing is at about 20,000 hertz, so that's 2.0 times 10 to the fourth hertz. And they're asking us to find the wavelength at the lower end of the range and the wavelength at the upper end of the range. If I have the frequency and I'm looking for the wavelength, I know I'm going to want to use my wave speed formula. And the third part to that wave speed formula is going to be the speed of the wave, which I can get from the temperature. So I know in order to get the wave speed from my temperature does have to be in Kelvin and not degrees Celsius. So my first step here is to convert my temperature from Celsius to Kelvin. So to do that, it's a pretty simple operation. I simply take my temperature in degrees Celsius and add 273 Kelvin to that. So 20 degrees Celsius plus 273 Kelvin is going to equal 293 Kelvin. I can now take that temperature and plug that into my wave speed formula. So my wave speed formula is equal to 331 meters per second. Remember, this 331 meters per second is the speed of a sound wave at 0 degrees Celsius. So that times the square root of my temperature in Kelvin divided by 273 Kelvin. When I plug my Kelvin temperature into that formula, I'm going to get a speed of the sound wave at 20 degrees Celsius of 343 meters per second. One quick note on this. You're going to see 343 meters per second come up a lot in these problems. And that is because 20 degrees Celsius is what is commonly referred to as room temperature. So that's kind of the standard room temperature, or the default temperature. When people say room temperature, they usually mean 20 degrees Celsius. So now I have the wave speed. I can now plug that into my wave speed formula and solve for the hertz. So my wavelength at 20 hertz, which is the lower end of my hearing range, is going to be 343 meters per second divided by 2.0 times 10 to the first hertz, and that is going to give me a wavelength of 17 meters. The wavelength at 20 kilohertz or 20,000 hertz is going to be 343 meters per second divided by 2.0 times 10 to the fourth hertz, and that is going to give me a wavelength of 1.7 times 10 to the minus second meters, which would equal 17 centimeters. So the wavelength for the range of human hearing is going to be from 17 centimeters to 17 meters. Part B of question 2 asks, what is the wavelength of a 1.0 times 10 to the first megahertz ultrasonic wave? Again, we're going to assume this is at room temperature, just like part A. So to find the wavelength at 10 megahertz, I know that I'm going to use my velocity of 343 meters per second and divide that by the frequency 1.0 times 10 to the 7th megahertz, because remember mega is 10 to the 6th, so I have to add that 6 to the 1 right here, and I will get 10 to the 7th hertz. And when I do that multiplication out, I will get a wavelength of 3.4 times 10 to the minus 5th meter. Problem 3 asks, calculate the percent error made over 1 mile of distance by the 5-second rule for estimating the distance from a lightning strike if the temperature is A, 30 degrees Celsius. So if you've ever used the 5-second rule to determine how far away a lightning strike is, essentially what you do is when you see the flash of lightning, you start counting Mississippis, and for every 5 Mississippis, that is supposed to equal 1 mile of distance. Assuming, of course, that the flash of the lightning can travel almost instantaneously, because that is traveling as a light wave, and then the thunder is a sound wave which travels much slower. So to calculate the percent error, we need to know just how far away the lightning flash is going to be at 5 seconds. So my first thing I'm going to need to do is convert a mile to meters. So I want to convert my mile to meters, and when I do that, I'm going to have 1 mile is going to equal 1,610 meters. Now, if I want to calculate the speed of the sound wave at 30 degrees Celsius, first thing I'm going to do is convert my temperature of 30 degrees Celsius to Kelvin. So 30 plus 273 Kelvin will equal 303 Kelvin. I plug that into my wave speed formula, and when I do that, I will get a velocity of the sound wave of 349 meters per second. So at 349 meters per second in 5 seconds, the actual distance to the lightning flash is going to be 349 meters per second times 5 seconds will be 1,745 meters. So the 5-second rule tells us that it's 1,610 meters away. The actual distance when it's 30 degrees outside is going to be 1,745 meters away. Now let's calculate the percent error between those two values. The actual value is 1,745 meters. My experimental value is 1,610 meters, and that will give me a percent error of 7.7% at 30 degrees Celsius. For part B, they want us to calculate the percent error when the air temperature is 10 degrees Celsius. So we're going to do this the exact same way. The only thing that's going to be different is that now, because the temperature is different, the speed that the sound wave is traveling is going to be different as well. So let's calculate that first. So at 10 degrees Celsius, I know that my wave speed is going to be 331 meters per second times the square root of 283 Kelvin divided by 273 Kelvin. And that will give me a wave speed of 337 meters per second. So the actual distance to the lightning flash is going to be my wave speed of 337 meters per second times my 5 seconds, and that will give me a distance of 1,685 meters. So again, to calculate my percent error, my actual value in this case is 1,685 meters. My experimental value is still 1 mile, which is 1,610 meters, and that will give me a percent error of 4.5%, which is a little bit lower than my percent error at 30 degrees Celsius, which was 7.7%. So the colder it is outside, the closer you are to having the 5-second rule be accurate when it comes to lightning flashes. Cool fact. Problem number 4, we're going to change gears for a moment here. Estimate the power output of sound from a person speaking in normal conversation using table 12.2 from the PowerPoint, and that is from the section on intensity in the PowerPoint. Assume the sound spreads roughly uniformly over a sphere centered on the mouth. So the distance for a normal conversation that we're going to use is 50 centimeters, which is equal to 0.50 meters. The intensity of normal conversation at that distance is 3 times 10 to the minus 6 watts per square meter, and that is what I got from the table. So this value I got directly from table 12.2, and we are trying to solve for the power. I know I'm going to need the area of the sphere at 50 centimeters. So the area of a sphere, which if you don't know that by heart, and you probably don't, but you can look it up because you got plenty of spare time. The area of a sphere is 4 pi r squared. So when I do that out for my 50 centimeter sphere, I'm going to get an area of 3.14 square meters. Now I can calculate the power. I know that the intensity of the sound wave is equal to the power divided by the area. So that means that my power is going to equal the intensity times the area. So my intensity of 3 times 10 to the minus 6 watts per square meter times my area of 3.14 square meters will give me an intensity of 9.425 times 10 to the minus 6 watts, or to one significant figure, 9 times 10 to the minus 6 watts. Problem number 5, last one. A sound wave has a frequency of 700.0 hertz and a wavelength of 0.50 meters. What is the temperature of the air in degrees Celsius? We are given the frequency of the sound wave, 700.0 hertz. We are given the wavelength of the sound wave at 0.50 meters, and we are being asked to find the temperature in degrees Celsius. So in order to find the temperature, I know I'm going to need the wave speed. I'm not given the wave speed, but I am given the frequency and the wavelength. And from those two factors, I can find the speed of the wave using my wave speed formula. So the speed of my sound wave is equal to the frequency times the wavelength. So 700.0 hertz times 0.50 meters will give me a wave speed of 350 meters per second. Now I can plug that into my wave speed formula, and when I plug that in, I am going to get a temperature of 305 Kelvin. And remember that you are always going to have to use the Kelvin temperature when you use this formula. You cannot plug a Celsius temperature into that formula, or when you solve for temperature, you will always have your temperature in Kelvin. So I need to convert that to Celsius. And to convert from Kelvin to Celsius is a pretty simple operation. Again, I just have to take my Kelvin temperature, subtract 273 Kelvin from that. So 305 minus 273 will give me a temperature of 32 degrees Celsius.